Hi and welcome everyone to one more lecture of probability and statistics. Today we will learn about estimators. First of all, we need to memorize some terms. First of them is a parameter. Parameter is a characteristics that is calculated using entire population. A parameter is a characteristic that is calculated using entire population. Example: population mean and population variance. Our next term is a statistic. Statistic is a characteristic that is calculated using sample population. Its example is sample mean and sample variance. Our population mean is denoted by mu. Our population variance is denoted by sigma square. Our sample mean is denoted by x bar. And our sample variance is denoted by S square. Now, our next term is estimator. Let's say I have a sample of x1, x2 till xn. These are random variables and I have a sample of these. And if I build a function, say Tn, which is a function of x1 to x1, x2 till xn, these random variables, it is a function of them. Then, if it is used to estimate the value of an unknown parameter theta is an unknown parameter. And if I use a function Tn, that is a function of x1, x2 till xn of these random variables, and if I estimate a value of unknown parameter theta using this, then this will be called an estimator. And the particular value that is estimated using this function or estimator will be called estimate. So these were the terms that we should know before starting with estimators. Now, estimators have certain properties which are first is unbiasedness. Second is consistency. Third is sufficiency. And fourth is efficiency. If estimator have a property unbiasedness, then we will call this unbiased estimator. If it have properties of consistency, then we will call it consistent estimator. And if it have a property of sufficiency, then we will call this sufficient estimator. And if this estimator have a property of efficiency, then we will call it efficient estimator. In this lecture, we will talk about unbiasedness and unbiased estimators. If we have a function Tn of x1, x2 till xn, these random variables, that is an estimator of theta. Tn will be an unbiased estimate of theta if expectation of Tn equals to theta. Our Tn function, which is a function of x1, x2 and xn till xn random variables, it will be an unbiased estimator if its expectation equals to our unknown parameter value. If expectation of Tn is greater than theta, then this estimator will be positively biased estimator. And if expectation of Tn is less than theta, then this will be negatively biased estimator. Now we will solve some questions on unbiased property of estimator. Our question is, if x1, x2 till xn is random sample from a normal distribution and mu1, where its mean value for normal distribution is mu and variance is 1, show that t equals to 1 by n summation I equal to 1 to n xi square is an unbiased estimator of mu square plus 1. First of all, this sample is taken from a normal distribution whose mean is mu and variance is 1. Therefore, expectation of xi will be equal to mu and variance of xi will be equal to 1 for I equal to 1, 2 till n. Now, we know that variance of xi equals to expectation of xi square minus expectation of xi whole square. Variance of xi is equal to 1, expectation of xi square as it is, minus value of expectation of I, mu. So this will be mu square. Now, expectation of xi square will be equal to 1 plus mu square. Now, our function is t equals to 1 by n summation I equal to 1 to n xi square. If it is an unbiased estimator, then expectation of t should be equal to 1 plus mu square. Expectation of t will be equal to, first of all, we know that expectation of ax, where a is a constant, equals to a times expectation of x. So 1 by n will be out of this expectation, integration summation expectation of xi square where I is equal to 1 to n. Now, we know that for every exi, expectation of xi square equal to 1 plus mu square. So, expectation of t will be equal to 1 by n summation I equal to 1 to n 1 plus mu square. Now, 1 plus mu square, this is a constant because these two values are known to us. And summation of a constant n times will be equal to 1 by n 1 plus mu square times n. And will got cancelled out. And our expectation of t will be equal to 1 plus mu square. And now that this holds, then we can say that t is an unbiased estimator of 1 plus mu square. So hence, our next question is, if t is unbiased estimator of theta, show that t square is biased estimator of theta square. First of all, we are given that t is unbiased estimator of theta. That means expectation of t equals to theta. Now, we know that variance of t will be equal to expectation of t square minus expectation of t whole square. Now, if we want to find out expectation of t square, this will be equal to variance of t, and we will take e of t square to the left side. So this will be plus e t whole square. Now we already know that expectation of t is theta. So expectation of t square equals to variance of t plus theta square. Variance of t will be greater than 0. Therefore, e of t square will be greater than theta square. That means expectation of t square is not equal to theta square. That means t square is not an unbiased estimator of theta square. That also means that t square is a biased estimator of theta square. And we can note from here that t square is positively biased estimator of theta square. Our next question is, if x is binomial random variable, show that first p cap equals to x by n is an unbiased estimator of p. So for the first part, first of all, we know that if x is a binomial random variable, then mu will be equal to np. That means expectation of x equals to np. Now, p cap equals to x by n. And we have to prove that this is an unbiased estimator of p, where p is probability of success. Now, first we have to find out expectation of p cap. Expectation of p cap will be equal to expectation of x by n. And we know that expectation of ax equals to a times expectation of x. Using this property, expectation of p cap will be equal to 1 by n times expectation of x. And we already know that x is a random variable. Therefore, its expectation is np. So this will be equal to np divided by n. N to n got cancelled out. So this is equal to p. Now our expectation of p cap is p. Therefore, p cap is an unbiased estimator of small p. Hence proved. For our next part, again expectation of x will be equal to np because x is a binomial random variable. That means it follows binomial distribution. Our p cap is x plus under root n divided by 2 n plus under root n. Now we have to find out expectation of p cap. Expectation of p cap will be equal to expectation of this. Now we can write this as x divided by n plus root n plus n under root n by 2 divided by n plus root n. So for first part, this will be equal to expectation of x divided by n plus root n plus expectation of this. Now this term will be a constant, and expectation of a constant equals to that constant plus under root n by 2 divided by n plus root n. Now if we will put the value of expectation of x, so this will be equal to p plus root n by 2 divided by n plus root n, and this is not equal to p. Therefore p cap is an biased estimator of p because expectation of p cap not equal to small p. That's all. We will meet in our next lecture.